Hello again, and welcome back. If you've been watching Part A of the 2012 Intermediate Math Competition, we have now moved on to Part B, or rather, we're just about to start Part B. So let's take a look at the questions. Remember, in Part B, we need to give full solutions. We need to explain our reasoning. And fortunately, there are less questions, though. So we had 6 in Part A. We're only going to have 3 in Part B. Let's take a look at Part B of the 2012 paper. Alright, so here we go. And just at the start, they're saying, give correct solutions. Full solutions. Let's take a look at question number 1. So, Rowan is given a square grid whose side length is an odd integer. Okay. So immediately we're thinking numbers of the form 2k plus 1, 2n plus 1. The square is divided into 1 by 1 squares, just like we have shown here off to the right. Okay. Rowan shades each 1 by 1 square that lies along the 2 main diagonals, and does not shade any of the remaining squares. So here we have a good 5 by 5, so odd integer, divided into 1 by 1 squares, so there's going to be 5 squared, or 25 of them. And each of the main diagonals has been shaded. So question number 1, Rowan is given a square grid that is 7 by 7. How many 1 by 1 squares does he shade? Alright. So there's probably a couple ways we could try and do this question. We might just try reasoning, or we could probably just draw an example. That would suffice. So let's take a look here. Draw a little bit of an example. Yeah. So, just going to draw ourselves a 7 by 7. Doesn't have to be perfectly exact. If you're one of those people who uses a ruler to draw everything, these sorts of questions can actually slow you down. What do I keep hitting? So there's 4. Five. So we're going to need to extend a little bit. 6 and number 7. Alright, so that's 7 rows. Now we just need 7 columns. 1, 2, 3, 4, 5. We're going to need to extend these guys. What on earth do I keep hitting that does that? Okay, so we're at 5. Here's 6, and here's 7. And we can just tidy our little picture up a little bit. Alright, so Rowan shades everything on the main diagonals and doesn't shade anything else. So we'll just shade along the main diagonal, and then we'll be able to count up the number of shaded squares. So here's the first diagonal. So we have 1, 2, 3, 4, 5, 6, 7 already done. Here's 8, 9, 10, we don't need to shade this one again, so we skip over that one in the middle. $11, $12, and $13. And we might give a little bit of an explanation. So we might say something like, by the example above, we see Rowan shades $13 squares. Alright, so let's go back to the question, just double check. Rowan is given a 7x7 square grid. We drew that. How many 1x1 squares does he shade? We were able to accurately demonstrate that with a picture. Proof by picture, perfectly valid. Alright, so part B. Rowan is given a square grid that is 101 by 101, so we're not going to be able to draw this one. Explain why the number of 1x1 squares he shades is 201. Alright, so at this point we have two examples. We have the 5x5 example over here, where we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We skip over that middle one. And we have the example we just drew out, where we had 7 along the main diagonal, 1, 2, 3, 4, 5, 6, 7. And then we had 1, 2, 3, skipped over 1, 4, 5, 6. So it looks like to shade both diagonals, if we were to count them, so let's do a little bit explanation. So if we were to count the shaded squares in each diagonal, of the n by n, and we have to remember that n is going to be odd. We'd get n shaded squares, and that's, n squares shaded. So each diagonal consists of n squares, and we're shading each diagonal and only those diagonals. So each diagonal gives us exactly n shaded squares. So in total, how many shaded squares we have? Well, we should be able to just add them up. However, there's one square that we have in common, namely this middle square over here. So if we were just to count up 1, 2, 3, 4, 5, 6, 7, there's 7 in this diagonal, going from the top left to the bottom right, and there's 1, 2, 3, 4, 5, 6, 7 shaded squares from the bottom left to the top right. But we've counted the center square twice. So the center square is in both diagonals. So in fact, we shade n plus n. First n coming from one diagonal, the second n shaded squares coming from the next diagonal, minus 1 for that common square that we've counted twice. So in total, we get 2n minus 1. Now specifically, in this question, we're asked, about the 101 by 101 grid. Oh, that's an awful looking comma right there. So we're asked to explain why we would get 201 squares. So we just plug in our number n into our formula that we just got for all the diagonals. So 2 times 101, because that's our n value, minus 1. Alright, so let's take a look. Rowan is given a square grid, 101 by 101. Okay. Why does he shade 201 squares? Well, we've just explained. Not only that, we've come up with a formula for the number of shaded squares in any size odd grid. So we explain our formula, where it comes from, each of the diagonals contributing a certain amount. That center square counted twice. We get our general formula. And so for the specific case we're asked about, the 101, we simply plug it in, and we get 201 shaded squares, exactly what they asked us to explain. So, for the next part, let's take a look at question 1, part C. So Rowan is given another square grid with odd side length. Okay, again, they're mentioning odd numbers, so I'm thinking things of the form 2k plus 1. That might come in handy later. And the number of 1 by 1 squares he shades is 41. How many unshaded 1 by 1 squares are there in the grid? Okay, so we're given the number of shaded squares. Unfortunately for us, we just figured out a formula. Okay? So we can use this formula. So from the last question, if n is the size of our grid, and by size I mean side length, then 2n minus 1 is the number of shaded squares. Okay, we're given the number of shaded squares, but we don't know the size. We want to figure out the size. So we know 41 is going to be 2n minus 1. We just don't know what n is. So we can rearrange and we figured out the size of our grid because we had a formula for the number of shaded squares. We easily rearrange that, get 21 by 21. Okay, but that's not what the question's asking us. We're not asked for the size of our grid. We're asked now for the number of unshaded squares there are in the grid. Okay, but at least we have the size of the grid, and that can help us. If it was small enough, we could just draw it and count up the unshaded squares. But 21 is still kind of big to represent here. So let's think. We know it's a 21 by 21 size grid. So how many squares are there in total? And of those squares, it's the split between unshaded and shaded. Well, now that we know the size of the grid, we can figure out how many squares there are completely. And we already are given the number of shaded squares. So if we subtract the two, we should get our final answer. So 21 squared, that's 441. If you're not comfortable with that, you can easily work it out with calculators. Calculators are allowed on this competition. So that's how many squares there are total. Now the total number of squares is equal to the number of shaded squares plus the unshaded squares. Okay? And we know these two numbers. We know total squares and we know shaded squares. There should be a plus sign there. I didn't see it for a second. So total squares, shaded plus unshaded. We know the total squares. We just figured that out. It's 441. We know this number of shaded squares. We were given that in the total in the question. So the total subtract shaded should be the unshaded squares. So it's 441 total. We know there's 41 shaded squares. That's what we were given to start off the question. So now we just explain. Alright. So notice how we've explained our reasoning here. If n is the size of the grid, we know 2n minus 1 is the number of shaded squares. We're using previous work. We calculate the size of our grid, and then we explain how that gives us the total number of squares. We make the observation the total squares is the same as the shaded squares plus the unshaded squares. We rearrange that equation, plug in information we already knew, and we were able to figure out that there are 400 unshaded squares. And that should conclude part C. Part D. So the last part in this question, this first question in B part, Rowan is given a fourth square grid. We've already dealt with a number of them. And it's obviously got odd side lengths, so we're still fine. Still working with things like 2k plus 1. I'm hopeful that that will come into some formula at some point. After shading the squares and the diagonals, there are 196 unshaded 1 by 1 squares. How many 1 by 1 squares does this grid contain in total? Okay. So now we're being told not the number of shaded or the number of total, but the number of unshaded. So in the last question, what did we do? We were given the number of shaded and we were able to figure out the total. Okay. How did we do that? Well, we had some sort of formula. Okay. Do we have a formula for the unshaded squares? Not yet, but maybe we can work one out. Okay. As we just remarked, the total squares is equal to the shaded squares. So total is equal to shaded plus unshaded. Okay? So if we just say n is the size of the grid, we don't know exactly what it is. So we know 2n minus 1 is the number of shaded squares. Okay? We also know, since it's an n by n grid of squares, that there's going to be n by n total number of squares. Okay. So we know the total, we know the shaded, just in terms of the size of our grid, but none of that's useful because we only know the unshaded. But if we rearrange, the number of unshaded squares is the total number of squares minus the shaded squares. Well, we have formulas for this side. N squared minus 2n minus 1. Which, of course, is n squared minus 2n plus 1. So now we have a formula in terms of the size of our grid for the number of unshaded squares. And we were given that. Okay. So we know that this formula holds. And now what do we need to do? Well, we need to figure out the total number of squares. That's what the question's asking us for. So if we were to figure out n, we would just need to square it, because n squared is the total number of squares, as we remark over here on the left. So we've set up this equation. We'd like to solve for n. So there's two ways we can go about doing it. We could use the quadratic formula. Right, we'll bring this 196 over here. We'll get n squared minus 2n minus 195 equals 0. Use the quadratic formula. We can solve for n. We know n will have to be positive. Or what we can do is observe that this is a very common formula. And it happens to be n minus 1 squared. This sort of formula pops up a lot. N squared minus 2n plus 1. That's n minus 1 squared. N squared plus 4n plus 4, that's n plus 2 squared. Things like that, just going to have to sort of get used to. It makes things a lot faster. But if we didn't realize that, if we didn't notice that it's already a square, we could rearrange and use the quadratic formula. So whatever you're more comfortable with, if you like the quadratic formula, by all means, go ahead. So 196 is n minus 1 squared. So the square root of 196 is going to be n minus 1. But 196 is already a perfect square. In fact, it's 14 squared. Okay. You could punch that into your calculator if you were a little unsure. So now if we rearrange this equation, we bring the minus 1 over here, we get 15 is equal to n. So our grid is going to be 15 by 15. So if we were to plug this into the total number of squares formula, you see that there are n squared, which is 15 squared, which you can do on your calculators, 225. Squares in the grid. So we just double check that we answered everything we were asked here. After shading the squares on the diagonal, there are 196 unshaded squares. How many 1 by 1 squares does the grid contain in total? Well, we figured that out. There are exactly 225. Okay. If you wanted to do another little check here, making sure that your number n equals 15 is correct, this is just a little side calculation, you could check to make sure that the number of shaded squares really does work here. So that shaded squares, we can calculate that in two ways. We can use the n we've got and plug it into 2n minus 1, and we should get 29 squares. Or you can also realize that it should be 225, the total number of squares, minus 196. So you can calculate it two different ways just to make sure your arithmetic hasn't screwed up. Either your value of n is fine, or your calculation of 225 at the end is correct. Either or. It's just a little check you can do just to make sure that everything's worked out, but we didn't stumble into any major roadblocks. There weren't a whole lot of arithmetic problems. This is the sort of thing you might want to check more if you used the quadratic formula rather than this n-1 squared formula. Just because more calculation problems can occur in the quadratic formula. But either way, so either do it or not, check it or not. We're moving on to question number 2. Feeling confident, feeling good. So I'll join you guys for question 2, which appears to be about lines and coordinates on a grid, but we'll dive into that next time.